All right. So is this review material for a final?
Yeah.
When's your final?
Next
week, or is it this week?
Yeah, it's next week.
Next week, okay. All right, so here's all the formulas for you to memorize. All right, let's see if we can pull off this graphing by remote, which isn't terribly easy to do, but you can describe to me how I would graph this. What's the elementary function in number 1?
Wouldn't it be just 1 to the x?
It's 2 to the x.
It is 2 to the
Yeah, I mean, I guess. This is just, you have various things. These are all pretty much the same. And the reason they're all pretty much the same is because they're all going to look like, hold on. In other words, it would be tough to distinguish the appearance of one from the other. Which one is that?
Can't really tell.
No. What's this point on all three?
Oh, positive 1.
Well, it's 0, 1. In other words, whenever you have an exponential equation like this, where the variable is in the exponent, whenever x is 0, this thing, the y value is 1 on all three of these. So the only real difference is y equal 2 to the x might be that curve. The middle curve might be y equal e to the x, and the other one is probably going to be like that, y equals 17 to the x. So the only difference is their steepness. Okay. Now, we'll leave that one up. How does this differ from this? What kind of transformation is taking place so that I can graph y equal 2 to the x plus 1?
Isn't it moved left 1?
Not left, vertical. This is a vertical shift. Okay. Up 1. If it was a minus 1, it would be down 1. Okay. So if I'm going to draw this curve, it's going to be exactly the same shape as the curve I have on here, only it's going to be up 1. Which means this key point here is now 0, 2. And its horizontal asymptote is at y equal 1, not y equals 0.
All right.
What's its domain here? Let me write it. Y equal 2 to the x plus 1. What is its domain?
Would that be all reals?
Yeah. And you can kind of see that from the graph. In other words, domain is the allowable values for x, and we certainly go to negative infinity that way, and we can go to positive infinity that way. In other words, there's no restriction on what I can put in for x. There's no value for x that violates any rules of mathematics. What is the range?
Is it positive 1 to infinity?
Parentheses or brackets?
parentheses.
On both, yes. And the reason is that this value right there can never be negative. In fact, it can never be 0. There's no value for x that makes this thing equal to 0 or negative. So at best, if I put in x of minus a trillion, it would get close to 0. That's why the graph looks like this. As I go to the left, it gets closer and closer to this line, this horizontal asymptote, which is the 1 part of it.
All right.
So the range is what again?
It would be parentheses 1, comma infinity.
Okay. And what's the transformation from the elementary function?
Up 1.
Vertical shift up 1. Right. What's the elementary function here?
Which would be 2x.
No,
Or 2 to the power of x.
well, it would be 1/2 to the power of x.
Okay.
Okay? Only because we have a 1/2 there and we got an x minus 1, but if I'm looking for an elementary function that's being transformed, it would be 1/2 x. Now,
All right.
when the number in the parentheses is less than 1, it no longer looks like this. What happens as x gets bigger is the thing gets smaller. However, it still goes through this key point, 0, 1. But instead of looking like it did, it now looks like this. As x gets bigger, it goes to 0. Notice that when x is 2, this becomes 1/4. When x is 3, it becomes 1/8. When x is 4, it becomes 1/16. Keeps getting smaller and smaller and smaller. Okay? So, the key thing to remember here is that when the number inside the parentheses is greater than 1, it's going to increase. When the number inside the parentheses is between 0 and 1, it's going to decrease. Now, we have 3 things going on here. Well, before we talk about those 3 things, let's talk about the domain and range of this function. What's the domain? The elementary?
All reals.
What's the range?
0 to infinity.
Good. Now, what 3 things are going on here?
Isn't it a vertical stretch by 4?
Good. Which basically means that every single point on this curve goes up by 4. In other words, this point that's at 0, 1 goes up to 0, 4. If I was only doing a vertical stretch.
All right.
What's the effect of the x minus 1 in the parent or as the exponent?
Is it move right 1?
Very good. And what's the effect of the minus 2?
Down 2.
Okay. So let's take the 1 point we know that's on this curve, 0, 1, and let's move it to the right by 1, first of all, and then down by 2. So that point that normally would be right here is now going to be down there. And what's the new horizontal asymptote?
It'd be -1.
-2. In other words,
-2.
yeah, the horizontal asymptote of this elementary function is y equals 0. So if we're shifting everything down by 2, then the new horizontal asymptote is going to be y equal 2. Or, excuse me, -2. And the new function is going to look a lot like our old function, only it's going to be a little steeper because of this 4. But it's got to go through this x. So I'm going to guess that it looks something like this, approaching the asymptote. Now, what would the y-intercept be? In other words, there's only 2 key points on this function. We've got, well, there's 3 key points. We've got this one. We know that that is shifted right by 1 and shifted down by 2. Hold on. Let's see, that's 0, 1. So if we shift it down by 2, it's going to be 0, -2, or -1. I wrote that incorrectly. That point right there is 1, -1. Because it shifted to the right by 1 and it shifted down by 2. Now, there are still 2 other key points on this thing. There's the y-intercept and there's the x-intercept. Well, how do we get the y-intercept? Here, let me write the function. The y-intercept is where with regards to x?
When x equals 0.
Okay, so plug in x equals 0 into this function, and what is y? What's 1/2 to the -1?
Isn't it 2?
Yeah, very good. 2 times 4?
8.
-2?
4.
Well, 6. 8 minus 2 is 6. So this y-intercept, which I haven't drawn very accurately, but we can certainly label, that's 0, 6. Okay? Now the x-intercept is a little harder. How do I get the x-intercept?
Y equals 0.
Correct. So I'm going to solve this equation. I'm going to set y equals 0. The first step is going to be to move that 2 over. So I'm going to have 2 equals 4 times 1/2 to the x minus 1. And I need to solve that for x. So what's the first step in solving that algebra? Actually,
divide by 4.
Yeah, it's actually not algebra. It's an exponential equation. It's not an algebraic one. How do I solve that for x? What's the next step? Oops, hold on. This thing is in parentheses, but it's okay. What's x? If I have 1/2 equals 1/2 to the x minus 1, what has to be true about x minus 1? What does it have to equal?
1.
Correct. Because this has a hidden exponent of 1 on it. And if 1/2 to some exponent equals 1/2 to x minus 1, then that some exponent has to equal x minus 1. So x equals what?
2.
Okay. So the x-intercept actually comes over here at 2. That point is 2, 0. So I really misdrew this graph when I drew it. I didn't draw it anywhere near steep enough. It's got to go through a y-intercept of 6. It's got to go through an x-intercept of 2. So, must look something more like this. Really steep. Still has to be asymptotic with that thing. All right. And that's everything there is to know about that function. In other words, we've talked about the domain, we've talked about the range, and we've talked about the transformations. It's the elementary function here.
Is it just log of x?
And that looks like a log function comes up from negative infinity, and then it gets very flat. It's not so flat that it stops rising. There's no horizontal asymptote on this thing. In other words, as x goes to infinity, y goes to infinity. But this thing is the inverse of 10 to the x. In other words, if I wanted, well, let's not go there, I guess, for the moment. But all of these log functions go through this key point, 1, 0, just like all of the exponential functions went through the point 0, 1. The log function is the inverse of an exponential function. So if I was going to draw an exponential function, it would look like that. And the log function is reflected about the line y equal x.
All right.
Okay, just worth knowing. Don't really have to know it for this problem, but it's very much worth knowing. That's why it goes through this key point, 1, 0, just like the exponential function goes through 0, 1. What is the transformation here?
Is it right 2?
Very good. So, in other words, it's going to go through that point right there, 3, 0. And there is a vertical asymptote on this function. Where's the vertical asymptote of the elementary function?
No, I'm just 0.
Correct. Where's the vertical asymptote of this transformed function?
2.
X equal to.
Yeah.
In other words, it's not a point, it's a line. Okay? What is the domain of the elementary function? Of this one right here.
Is it 0 to infinity?
Parentheses or bracket?
Parentheses.
Yes. In other words, you cannot take the log of 0. Ever. It's more restrictive than the square root function is. In other words, if I have y equals square root of x, x could be 0 or positive. But if I have y equal the log of x, x can only be positive. It can't even be 0. So what's the domain of this function? The transformed.
2 to infinity?
Very good. With parentheses, correct. And what is the range of this function?
All real.
Very good. You already said the transformation, so we can go to 4. What'd you do when you took this picture?
Oh no, my phone gets really weird.
Oh, okay.
It'll auto zoom.
I can't read the base here. What's the base on this log?
3.
3?
Yeah.
And then it's x plus 3. Yeah, like that. Okay. What's the domain of this function?
Would it be -3 to infinity?
Well, no, this is not in parentheses. That would be the correct answer if it was like that. But I don't see any parentheses, so this plus 3 at the end is a vertical shift. It's not a horizontal shift.
Alright.
Okay?
So it's 0 to infinity.
Yes. What's the range?
All reals.
And what is the transformation?
Is it up 3?
That's it. And in fact, log functions are very similar to exponential functions. If I draw it like that, you're going to have a hard time telling me whether that's log base 3, log base 2, log base 18, because they're all going to go through this point right here, 1, 0. Now, to transform it up 3, I take that point, 1, 0, and I move it up 3. So our transformed function is going to go through what point?
1, 3.
We're moving it up 1, 3. You're correct. Excuse me. I was incorrect thinking about it. 1, 3. And it's going to look like this. I suppose the other point that might be worth knowing is the x-intercept. How would I find that? In other words, the only point on this curve that's more interesting than the 1, 3 is where does it cross the x-axis? Do you have to know that? I mean, it says graph it, but
I'm not really sure.
All right. Well, if I had to know what that point is, that's where y is equal to 0, so I would have to solve this equation, which means log base 3 equals log base 3 of x. How do I solve that equation?
Don't you take log of -1? No. I don't remember.
You would exponentiate each side to whatever base you have. In other words, if I'm trying to solve this equation and I take the right side and I make it the exponent to the number 3, I can do that as long as I take the left side and make it to the exponent of the number 3. You see what I'm doing there?
Yeah.
Okay, let's erase everything else here so we know what we're doing here. So that's how I'm going to solve this. And the reason is what does the right side become?
X.
Exactly. What's the left side become?
Is it just -9?
No.
No, that doesn't.
Remember that negative exponents do not mean negative numbers. It means reciprocals.
Oh, yeah. So
minus 3 equals what?
120.
1/27th is exactly right. Okay?
Yep.
Oh, now it's getting clear. Maybe you were at
Well,
an angle or something. So let's make sure that you can go back and forth between exponential and logarithmic. That's one of the most important things you can do. Okay, so how do I write that logarithmically?
Is it just for is log equal to 2 log base 2 of 4?
No. Remember one statement. Logs are exponents. That's all you have to remember. Logs are exponents. So what goes on the right side of my equal sign?
16.
Which is the exponent?
2.
That's what goes on the right side of my equal sign. Logs are exponents. Now, what's going to be the base down here of my log?
4.
Yeah, I knew you'd get that. And the only other place for the other number is 16. That's the logarithmic expression. And like I said, as long as you remember that logs are exponents, you immediately start this way. And then you know the base is always that. And there's only one other place for the third number, and that's as the argument. So that's kind of the way you want to remember how to do these. And then if you're going from logarithmic to exponential, I do have a way that I do it. I take the number on the far left, raised to the power of the number on the far right, equals the number in the middle. So it would be 4 squared equals 16. Write this one logarithmic.
Right. Oh, okay.
2 to the x equals 9.
So it'd be log base 2 of 9 equals x.
You got it. Write in exponential format, number 7.
So it'd be
Take the number on the far left.
so it'd be 5 to 5 squared equals 25.
Very good. And number 8. Guess that's a b.
Yeah, it's a b. So b to the y equals x.
Very good. What's the log of 1/10 equal to? What's the base on this?
10.
Okay. So express this exponential. Let's make it equal x, since we're trying to find out what it's equal to. And now express that exponentially for me.
Ten to the x equals 1/10.
What's x going to be?
-1.
You got it. What's the natural log of e equal to?
Is it a number?
Well, yeah, let's see. In other words, let's let it equal x and then solve for x. What's the base of natural log?
10.
It's e.
Oh.
The base of log is 10, if they don't state it otherwise. But when you see natural log, its base is e. So now express this exponentially.
So e to the x equals e.
What's x?
Oh, x.
X got to be.
1.
Right. And in fact, if I have log base b of b, that's always equal to 1 no matter what b is.
All right.
Okay? Mitch, sorry, I gotta go. I got a 4:30.
All right.
I will talk to you later. Hopefully that's been helpful. I think it has.
Yeah.
Okay. Bye-bye.